hangs in the night sky like a lantern someone forgot to turn off. Before we go any further, if you want a brand new space topic every single night to fall asleep to, subscribe. One tap and a new story is waiting for you every evening. It is the brightest object in our night sky, and it has been watching over this planet for longer than any living thing has existed on it. For most of human history, we looked up at the moon and thought we understood it. We saw a dry, silent, airless world, a place of gray dust and ancient craters, a place where nothing flowed, nothing changed, and nothing could survive. Scientists called it bone dry. Textbooks described it as one of the most barren places in the entire solar system. They were wrong. Hidden in the darkest corners of the moon, tucked away in places where sunlight has never once touched the ground, there is water. Real water. Ice, locked into the soil, waiting quietly in the cold. It has been there for billions of years, and for most of human history, we had no idea. That discovery changed everything we thought we knew about our closest neighbor in space. The moon is about 239,000 miles from Earth on average. That is close in space terms. You could fit all the other planets in our solar system in the gap between Earth and the moon, and still have room left over. It is so close that on a clear night, you can see its mountains and craters without a telescope. It feels familiar. It feels known. And yet, for decades, scientists were certain it held no water at all. The reason for that certainty made sense at the time. The moon has almost no atmosphere. An atmosphere is the layer of gas that wraps around a planet and protects its surface. Earth has a thick one. The moon's is so thin it barely counts. Without that protection, the moon's surface is exposed to the full force of the sun. Temperatures on the sunlit side can climb to 260 degrees Fahrenheit. That is hot enough to boil water away in seconds. So the thinking was simple. Any water that ever reached the moon would have been cooked off long ago, evaporated, gone, lost to space forever. But the moon is also a world of extremes. On the side facing the sun, the heat is fierce. On the side facing away, the cold is almost impossible to imagine. Temperatures in the deep shadows of certain craters near the moon's poles can drop to negative 400 degrees Fahrenheit. That is colder than the surface of Pluto, colder than almost anywhere else in our entire solar system. In those frozen shadows, the rules change completely. The moon's axis, which is the imaginary line it spins around, is tilted at just about 1.5 degrees. Earth's axis tilts at about 23 degrees, which is why we have seasons. The moon's tiny tilt means its poles receive sunlight at an extremely shallow angle, almost sideways. Some craters near the poles have rims tall enough to block that low sunlight entirely. The floors of those craters sit in permanent darkness. They have not seen a single ray of sunlight in potentially billions of years. Scientists call these places permanently shadowed regions. And inside them, the cold is so deep and so stable that water ice can survive indefinitely. Not for years, not for centuries, for billions of years. The moon we thought we knew was a dead, dry rock. The moon we are still learning about is something far more interesting. It is a world that has quietly collected and stored water over an immense stretch of time. It gathered that water from comets, from asteroids, from the solar wind, and possibly even from its own ancient volcanic past. And it hid that water in the coldest, darkest places it could find. This episode is about that water, where it came from, how it survived, what it looks like, and why it matters so much for the future of human exploration. We are going to move slowly through all of it. There is no rush. The moon has been keeping these secrets for billions of years. We have all night to learn them. So settle in. Let your breathing slow. Picture the moon above you right now, pale and quiet and full of hidden things. It is closer than you think, and it is far stranger than anyone once believed. The story begins with the first hints that something was there, waiting to be found. For a long time, scientists were certain about the moon. It was dry. It was barren. It had no weather, no rivers, no rain. Every sample the Apollo astronauts brought back in the late 1960s and early 1970s seemed to confirm this. The rocks were bone dry. The dust was bone dry. The moon, as far as anyone could tell, was one of the driest places in the entire solar system. That certainty held for decades. Then, slowly, the evidence began to shift. The first real crack in the old story came from an unlikely source. In 1994, a spacecraft called Clementine orbited the moon. It was not designed specifically to look for water. Its main job was to map the lunar surface and test military sensor technology. But while it was up there, circling the moon in the dark, it picked up something strange. Radar signals bouncing back from the South Pole behaved differently than expected. Something near the pole was reflecting radar in a way that dry rock simply does not. Scientists were cautious. They did not rush to announce a discovery. Radar can behave oddly for many reasons, but the signal was interesting enough to keep looking. Then came Lunar Prospector in 1998. This spacecraft carried a special tool called a neutron spectrometer. A neutron spectrometer detects hydrogen by measuring the way neutrons, tiny particles given off by cosmic rays hitting the surface, slow down when they pass through hydrogen-rich material. Hydrogen slows neutrons the way a pillow slows a thrown ball. And where there is hydrogen on a cold, airless world, there is a very good chance there is water. Lunar Prospector found hydrogen. It found it at both poles. The signal was strongest in the permanently shadowed craters, those deep, bowl-shaped regions near the poles where sunlight never reaches. The spacecraft could not see the water directly. It could only sense the hydrogen hiding beneath the surface. But the reading was clear enough that scientists began saying something they had not said before. There might be ice up there. Still, the word might carried a lot of weight. The instruments were good, but they were not perfect. The hydrogen signal could have come from solar wind particles trapped in the soil rather than actual water ice. Scientists needed more. They needed to get closer. They needed, in a sense, to taste the moon. That moment came in 2009, and it was dramatic. NASA deliberately crashed a spacecraft into a permanently shadowed crater near the moon's south pole. The mission was called LCROSS, which stands for Lunar Crater Observation and Sensing Satellite. The idea was simple but bold. Slam a heavy rocket stage into the crater floor at high speed gets kicked up. Then fly a second spacecraft through the debris cloud and analyze it before that spacecraft also crashes into the surface. The impact sent a plume of material shooting upward into the sunlight. Scientists watching from Earth and from orbiting spacecraft held their breath. And then the data came back. The plume contained water vapor. Real water. Not a trace. Not an ambiguous signal. But actual water molecules rising from the dark floor of a crater that had not seen sunlight in billions of years. The moon was not dry. It had never been entirely dry. The amount detected in that single impact was modest. Scientists estimated the crater's soil contained water ice at a concentration of roughly 5 to 8% by weight. Picture a handful of lunar dirt. If that dirt came from the right shadowed crater, nearly 1 in every 15 grams of it could be water. That is more than what you would find in the driest deserts on Earth. This was not a small finding. This was a rewriting of everything. What made it even more remarkable was the timing. These first signs of something hidden did not come from one mission or one discovery. They came from a slow accumulation of signals, each one building on the last. Clementine noticed something odd. Lunar prospector found hydrogen. LCROSS confirmed water. Each spacecraft handed the mystery forward, like a relay, across 15 years of careful work. Science often moves this way, not in a single flash, but in quiet steps. One instrument sees a shadow. Another measures a slowdown. Another flies through a cloud of ice and says, "Yes, it is here." The moon had been holding its secret patiently, and the scientists who found it were just as patient. They followed the faint signals across years and miles, and the cold silence of space, until the answer finally came clear. So now we know the water is there, but that raises a quieter, stranger question. How does water survive on the moon at all? Space is not kind to water. Out in the open, under the full glare of the sun, water molecules break apart almost instantly. Ultraviolet light, the same invisible radiation that sunburns your skin, carries enough energy to split a water molecule into its two basic parts. One, hydrogen, nothing more than scattered gas, lost to the void. This process is called photodissociation, which simply means light breaking something apart. On the surface of the moon, in direct sunlight, it happens fast. A water molecule exposed to the sun can be destroyed in a matter of hours. And yet the water is there. Hundreds of millions of tons of it, tucked into the soil, clinging to crater walls, hiding in the dark. Something must be protecting it. Something must be keeping it whole. The answer comes down to temperature. Specifically, to cold so extreme that it is almost hard to imagine. Water freezes at 0 degrees Celsius here on Earth. That is cold enough to turn a lake to ice. But the coldest places on the moon reach temperatures far below that. Some craters near the lunar poles drop to around -250 degrees Celsius. That is colder than the surface of Pluto. It is among the coldest natural environments in the entire solar system. At those temperatures, water does not just freeze. It locks in place. It becomes almost perfectly stable, held so tightly by the cold that even billions of years cannot shake it loose. The key is that these places never see sunlight. Not once, not ever. The moon tilts very slightly on its axis, only about 1.5 degrees. Earth tilts more than 23 degrees, which is why we have seasons. The moon's tiny tilt means that sunlight always hits its poles at an extreme angle, skimming along the surface like a flashlight held almost sideways. Tall crater rims catch that shallow light. The floors of those craters, sitting low and deep, never receive even a single ray. Scientists call these places permanently shadowed regions. They have been dark for billions of years. Some of them may not have seen sunlight since the moon itself was young. Inside those shadows, the cold is absolute. And inside that cold, water can survive. But surviving is only part of the story. The water also had to get there in the first place and stay there long enough to accumulate. This is where the physics becomes quietly beautiful. When a water molecule lands in a permanently shadowed region, the cold traps it immediately. It cannot evaporate. It cannot drift away. It simply stays, settling into the soil or freezing onto a grain of dust. Over millions and millions of years, molecule by molecule, the ice builds up. Scientists call this a cold trap, and that is exactly what it is. A place so cold that anything frozen that arrives there simply cannot leave. The moon's surface is not perfectly still, of course. Tiny meteorites strike constantly, kicking up dust and debris. Solar radiation pushes particles around. Water molecules that form or land in sunlit areas do get destroyed, just as quickly as the physics says they should. But some of those molecules, before they are lost, hop across the surface in tiny leaps. Researchers call this process thermal hopping. A molecule warms slightly, lifts off the surface for a fraction of a second, then lands again somewhere else. Most of them hop into sunlight and are gone, but a small number, through chance and geometry, hop toward a pole. They hop toward the shadow, and when they reach it, the cold catches them, and they stay. It is a slow process, enormously slow. But the moon has had an enormous amount of time. 4.5 billion years is long enough for even the smallest trickle to become a reservoir. What this means is that the water on the moon is not there by accident. It is there because the physics allowed it. Because the moon's gentle tilt created permanent shadows. Because those shadows created cold traps. Because the cold traps held on to every molecule that found its way inside. The whole system worked together, quietly and patiently, across timescales that dwarf anything in human history. The moon did not ask for its water. It simply created the right conditions, and the water came and stayed and waited, just as it is still waiting now, in the dark, in the cold, perfectly preserved. Those cold traps are remarkable places. They sit at the bottom of craters near the moon's north and south poles, and the temperatures inside them are so extreme that scientists have called them the coldest places in the entire solar system. That is not a small claim. The solar system contains gas giants with howling storms, moons drifting billions of miles from the sun, and clouds of frozen gas at the very edge of known space. And yet, the floors of certain lunar craters are colder than almost all of them. Inside the deepest, shadowed craters near the moon's poles, temperatures can drop to around -250 degrees Celsius. Celsius. That is colder than the surface of Pluto. It is close to what scientists call absolute zero, the lowest temperature that physics allows. At that temperature, almost nothing moves. Almost nothing changes. Time, in a sense, slows to a crawl. Water ice survives in those places because of simple chemistry. Water is made of two hydrogen atoms bonded to one oxygen atom. That combination, so common in the universe, is also remarkably stable when it gets cold enough. At those extreme temperatures, the molecules lock together and hold. They do not drift. They do not evaporate. They simply sit, frozen and still, waiting. The hydrogen and oxygen that make up that ice did not come from nowhere. Both elements are among the most common in the universe. Hydrogen was born in the first few minutes after the Big Bang, the enormous event that started everything. Oxygen came later, forged inside the cores of massive stars that burned bright and then exploded. When those stars died, they scattered their contents across space. That oxygen drifted for millions of years before it found its way into water molecules, into comets, into the early solar system, and eventually onto the moon. There is something quietly moving about that. The water locked inside a lunar crater today carries atoms that were born inside a star that no longer exists. The moon is holding onto pieces of the ancient universe, preserved in ice, in the dark. The soil around those craters also tells a story. Lunar soil, which scientists call regolith, is made mostly of oxygen, silicon, magnesium, iron, calcium, and aluminum. These are not exotic materials. They are the same basic elements found in rocks on Earth. The moon and Earth formed from the same cloud of gas and dust roughly 4.5 billion years ago. They share the same raw ingredients, but the moon has no atmosphere to protect its surface. No air, no weather, no erosion from wind or rain. What lands on the moon tends to stay on the moon, and what gets trapped in a cold crater stays there for an extraordinarily long time. Scientists believe some of the ice in those polar craters may be billions of years old. Not thousands, not millions, billions. It may have arrived early in the moon's history, when comets and asteroids struck the young solar system in enormous numbers. That period, which scientists call the Late Heavy Bombardment, was a time of constant collisions. Icy bodies from the outer solar system rained down on the moon, on Earth, on Mars, on everything. Some of that ice found its way into the shadows and never left. Ice that old would carry a record of the early solar system inside it. The chemistry of ancient ice can tell scientists what the solar system was made of long before Earth had oceans, before life began, before anything we would recognize existed. The moon's cold traps may be storing that record right now, perfectly sealed, waiting to be read. What makes those craters so effective as cold traps is not just the temperature. It is also the depth. Some of the craters near the poles are very deep relative to their width. The sun's light, which arrives at a low angle near the poles, cannot reach the bottom. The geometry works against the light. The crater walls block it completely, and the floor stays dark no matter what time of year it is, no matter where the moon is in its orbit. That darkness is total. No light has touched the floors of some of these craters for billions of years. They are among the darkest places in the solar system, not because of any special material, but simply because of their shape and their location. And in that darkness, the ice holds on, molecule by molecule, year by year, across timescales that stretch back to the earliest days of the solar system. The cold does not ask for anything. It simply keeps what it is given. And what it has been given, it has kept for an almost unimaginable length of time. The floors of those craters sit in a kind of permanent night, but the darkness alone is only part of the story. What truly makes these places extraordinary is the set of forces that created them and have kept them exactly as they are for billions of years. Gravity, geometry, and the slow tilt of the moon all work together, each one playing its part, each one reinforcing the others. Start with gravity. The moon's gravity is weaker than Earth's, about 1/6 as strong. That difference matters more than it might seem. On Earth, our stronger gravity holds a thick blanket of air around the planet. That air moves heat from place to place. It carries warmth from the sunny side to the dark side. It softens surface. It can only radiate straight up and out into space. So when a place on the moon falls into shadow, it gets cold very fast, and it stays cold. There is nothing to bring the warmth back. Now think about the moon's tilt. Earth is tilted about 23 degrees on its axis. That tilt gives us our seasons. The moon, by contrast, is tilted only about 1.5 degrees. That is an almost perfectly upright spin. Because of this, the sun never rises very high above the horizon near the moon's poles. It skims along the edge of the sky, low and flat. Its light arrives at a shallow angle, like the light of a winter sunset that never quite rises. For most surfaces near the poles, this means the sunlight is weak and glancing. But for the floors of deep craters, it means something more dramatic. The light never arrives at all. The crater walls catch it first. The floor stays in shadow forever. Scientists call this effect topographic shielding. The shape of the land itself acts as a shield. The taller and steeper the crater walls, the more completely they block the low-angle sunlight. Some of the craters near the moon's south pole, like Shackleton Crater, are roughly 21 kilometers wide and about 4 kilometers deep. That is a significant depth. The walls rise steeply, and the floor sits far below the surrounding terrain. Even if the sun were to shift slightly in the sky, the geometry would still protect the floor. The shadow is built into the shape of the place. These shadowed floors are so cold that scientists have measured temperatures there of around negative 173 degrees Celsius, and in some spots, even colder. That is close to negative 280 degrees Fahrenheit. At those temperatures, water ice does not melt. It does not even slowly drift away into space as a gas, the way it might in warmer conditions. It locks in place. The molecules slow down so much that they barely move at all. The ice becomes almost perfectly stable. There is something else at work here too. The moon's surface, called the regolith, is a loose layer of fine dust and broken rock. This material is a poor conductor of heat. It does not pass warmth down into the ground easily. So even if a tiny amount of heat arrived at the edge of a shadowed crater, it would not travel far. The regolith inside insulates the ice below it, the way a thick blanket keeps warmth in or cold out. Scientists believe that in some places, ice may be buried just beneath a thin layer of this dusty soil, protected from even the faint radiation that reaches the surface. All of these forces, the weak gravity that allows no air, the small tilt that keeps sunlight low, the steep crater walls that block it entirely, the bitter cold that freezes everything in place, the insulating dust that seals it in, they all point in the same direction. They all work to preserve what lands in these craters. Nothing escapes. Nothing changes. The ice that arrived here long ago, whether carried by a comet or built slowly by the solar wind, has nowhere to go. It is a remarkable kind of stillness. Not the stillness of emptiness, but the stillness of something held very carefully in place by forces that have been working without pause for billions of years. The universe can be violent and restless, full of explosions and collisions and change. But here, in these dark and frozen bowls near the top and bottom of the moon, something quieter has been happening, a slow, patient keeping, a preservation so complete that the ice inside may carry the chemical memory of the early solar system, untouched and undisturbed, waiting for the moment someone finally comes to read it. So the ice is there, held in place, preserved. But how did it arrive in the first place? That question takes us back billions of years to a solar system that looked nothing like the one we know today. The early solar system was a crowded and chaotic place. Rocks and ice and dust swirled around the young sun in enormous clouds. Slowly, over millions of years, gravity pulled those clouds together into planets and moons. But not everything found a home. Countless smaller objects, some no bigger than a house, some as wide as a city, kept moving through space on long, looping paths. Many of them carried water, not liquid water, but water locked inside rock and ice, frozen solid in the deep cold between the planets. The moon, in those early days, was a target. It had no air to slow things down, no ocean to absorb the impact. When something hit the moon, it hit hard. And scientists believe that many of those early impactors, the asteroids and comets that that struck the lunar surface over billions of years brought water with them. Each collision was a delivery, small, violent, and spread across an enormous stretch of time. To understand the scale of this delivery, think about a single grain of sand. Now imagine that grain landing on a football field, then another, then another. Over millions of years, the field slowly fills, one grain at a time. That is roughly how the water built up on the moon. No single event flooded it. No single comet filled the craters with ice. It happened slowly, patiently, one impact at a time. Across a span of time so long, it is almost impossible to hold in your mind. Scientists estimate that the moon has received impacts from water-bearing objects for roughly 4 billion years. 4 billion years is about as long as life has existed on Earth. It is long enough for single-celled creatures to become fish, for fish to become reptiles, for reptiles to become mammals, for mammals to become us. All of that change, all of that time. And the moon was quietly collecting water the whole while. The total amount of water ice that scientists believe exists on the moon today is estimated at roughly 600 million metric tons. That sounds enormous. And in one sense, it is. 600 million metric tons of water could fill about 240,000 Olympic swimming pools. If you lined those pools end to end, they would stretch from New York to Los Angeles and back again, more than twice. But spread across the surface of the moon, that water becomes very thin. The moon's surface area is about 38 million square kilometers. That is roughly the same as the continent of Africa and the continent of Australia combined. Spread 600 million metric tons of ice across that much ground, and it becomes a whisper, a thin, hidden layer mixed into the soil, tucked into shadows, scattered in patches that no human eye has ever seen directly. Most of that ice sits near the poles, concentrated in those permanently shadowed craters we explored in the last section. But even there, it is not a solid sheet of blue-white ice waiting to be scooped up. Scientists believe much of it is mixed into the top layer of lunar soil, called regolith, the loose, dusty, broken rock that covers the moon's surface like a gray blanket. ice is threaded through that soil, grain by grain, molecule by molecule. In some places, scientists estimate the concentration of water ice in the soil may be as high as 5 to 10% by weight. In other places, far less. 5 to 10% sounds modest. But consider this: that percentage is comparable to some of the driest deserts on Earth. Places like the Atacama in Chile, where scientists once thought nothing could survive, and where they later found life clinging to the underside of rocks, pulling moisture from the air. The moon's ice is sparse, but sparse does not mean useless. It does not mean small. It means patient. It means waiting. The water arrived slowly. It was preserved carefully. It sits now in the dark, in amounts that dwarf anything a single human mind can picture, yet spread so thin across such a vast and ancient surface that finding it took us decades of searching, and some of the most sensitive instruments ever built. The scale of it is both humbling and quietly wonderful. A vast amount of something precious, hidden in plain sight, delivered one small impact at a time across 4 billion years of silent, steady accumulation. Some of that water arrived the same way a gift arrives, carried from far away, across an almost unimaginable distance, by something bright and fleeting. Comets are ancient travelers. They are loose, frozen bodies made of ice, dust, and rock, born in the cold outer edges of our solar system billions of years ago. When a comet swings close to the sun, the heat causes its ice to turn directly into gas, releasing great glowing streams of vapor and dust that trail behind it like a long, pale veil. That glowing tail is what we see from Earth on a clear night. A soft smear of light moving slowly across the sky. But before a comet reaches the sun, before it begins to shed itself into that shining trail, it carries its ice intact. It carries it across the dark. Scientists believe that comets have been striking the moon for billions of years. The moon has no atmosphere to slow them down, no thick blanket of air to burn them up before they land. When a comet hits the lunar surface, it hits hard and fast, releasing enormous energy in an instant. The impact vaporizes much of the comet's ice, but not all of it. Some fraction of that water survives the collision in the form of vapor, rising briefly above the surface before the moon's weak gravity and the cold of space pull it back down. That vapor drifts. It hops across the surface, molecule by molecule, until it finds somewhere cold enough to settle. And the coldest places on the moon, as we have seen, are the permanently shadowed craters near the poles, where temperatures drop to around minus 250 degrees Celsius, colder than almost anywhere else in the solar system. There, the water freezes. It stays. Picture the lunar surface as it looks from just above. You are floating perhaps a kilometer up, drifting slowly over the southern pole. Below you, the terrain is ancient and battered. Billions of years of impacts have left the land cratered and rough, like the surface of something that has been through a great deal and carries the marks of it. The soil, called regolith, is a fine gray powder mixed with sharp-edged fragments of rock. It has no color the way Earth soil has color. It is pale and ashen, the gray of old ash or cold concrete, broken here and there by the white glint of exposed rock, where a newer impact has punched through the older surface. Near the poles, the craters grow deeper and more dramatic. Some of them are enormous, wide enough to swallow a small city, their walls rising in steep, jagged ridges. The sunlight catches the upper rims of these craters and turns them gold. But the floors stay black, perfectly black, the kind of black that has not seen light in billions of years. And somewhere down in that blackness, mixed into the fine gray powder of the soil, the ice sits quietly. You cannot see it from above. It does not glitter or shine. It is hidden inside the dust itself, frozen into the spaces between grains, invisible to the eye, but present, patient, real. Comets are not the only source of this ice, but they are one of the most dramatic. A single large comet impact could deliver a significant amount of water in one sudden, violent moment. Scientists estimate that comets may have contributed a meaningful portion of the total water ice now locked in the moon's shadowed craters, though the exact percentage is still a matter of careful study and ongoing research. What is clear is that the process has been happening for a very long time. The solar system is old, the moon is old, and comets comets have been crossing that ancient sky for nearly as long as the solar system has existed. There is something quietly moving about this. A comet forms in the cold dark beyond the planets. It travels for millions or billions of years. It swings inward toward the sun. It strikes the moon in a flash of heat and light. And some small part of it, some fraction of its ancient ice, survives that collision and finds its way into the permanent shadow of a crater, where it will remain for millions of years more, waiting. The water in those craters is not just water. It is a record. Each molecule carries a history, a story of where it came from and how far it traveled. The moon's surface holds that record in the dark, in the cold, in the silence. And we are only just beginning to learn how to read it. Comets are not the only travelers bringing water to the moon. There is another source, quieter and more constant, one that has been working without pause for billions of years. It comes not in a flash of light and heat, but in a slow and steady stream. It comes from the sun itself. The sun is always releasing a flow of tiny charged particles into space. Scientists call this the solar wind. It is not wind the way we think of wind on Earth. Nothing you could feel on your skin. It is more like a river of invisible energy, streaming outward in all directions from the sun at enormous speed. These particles travel hundreds of miles every single second. They reach the moon in just a few days. The moon has no thick atmosphere to stop them. On Earth, our atmosphere and our planet's magnetic field act like a shield, turning most of those particles away. The moon has almost no such protection. So the solar wind hits the lunar surface directly, striking the top layer of dust and rock with a steady, patient force. Now, the solar wind is made mostly of protons. A proton is one of the tiny building blocks inside an atom. And here is where something remarkable happens. The lunar soil contains oxygen, locked inside minerals in the rock. When a proton from the solar wind strikes that oxygen, the two can combine. A hydrogen atom bonded to an oxygen atom is the first step toward making water. Over time, this process builds up a very small amount of hydroxyl, which is a molecule made of one hydrogen atom and oxygen atom, just one step away from a full water molecule. This is not water pouring down from the sky. It is water being built, atom by atom, inside the surface of the moon, through a slow chemical process driven by sunlight. Scientists sometimes call this space weathering. The way the solar wind slowly changes the chemistry of the lunar surface over millions of years. The moon's skin is being quietly rewritten, one particle at a time. The layer where this happens is very thin. We are talking about the top few centimeters of the lunar soil, the part called the regolith, that loose, fine-grained layer of broken rock and dust that covers the moon's surface like a soft gray blanket. The regolith is the moon's outermost skin, and it holds a great deal of information about what has struck it and what has settled into it over billions of years. What happens to this solar wind water after it forms is still a matter of active research. Some of it likely escapes back into space, lost to the vacuum. Some of it may be broken apart again by the sun's ultraviolet light, the high-energy rays that bake the surface during the long lunar day. But some of it, scientists believe, may migrate. Water molecules on the surface can move when they are warmed, hopping slowly across the ground in tiny jumps, drifting toward cooler places. And the coolest places on the moon are those permanently shadowed craters near the poles. This means the solar wind may be feeding those cold traps, adding a slow trickle of new water molecules to the ice already stored there. Comets deliver water in dramatic bursts. The solar wind delivers it quietly, constantly, in amounts so small they are nearly impossible to measure directly. But over billions of years, even the smallest trickle adds up. There is something worth sitting with here. The sun, which we think of as the great destroyer, the source of heat and radiation that bakes the lunar surface and strips away molecules, is also, in a very real sense, a builder. Its particles strike the moon and help create the very water molecules that then hide from its light in the deepest shadows. The sun gives, and the sun takes away. And somehow, in the balance between those two forces, water survives. The deeper you look at the moon, the more you find that nothing works in isolation. Comets bring ancient ice from the outer solar system. The solar wind builds new molecules from the soil itself. Craters trap and preserve what arrives. The sun's light drives some water away and helps other water migrate to safety. Each process connects to the others, each one part of a larger system that has been running quietly for billions of years. The moon looks still and silent from here, but beneath that gray surface, in the chemistry of its dust and the cold dark of its craters, something has been happening all along. The universe has been doing its slow, patient work, and the water it has made and moved and hidden is still there, waiting in the dark. There is one more source of water on the moon that often gets overlooked. It is older than any comet impact. It is older than most of the craters we can see from Earth. It comes from the moon itself, from deep within its ancient body, from a time when the moon was not the quiet gray world we know today. Billions of years ago, the moon was alive with fire. In its earliest days, roughly 3 to 4 billion years ago, the moon experienced enormous volcanic eruptions. Vast rivers of molten rock, called lava, poured across its surface. These eruptions built the dark, flat plains we can still see today. The wide, smooth regions called Maria, which is the Latin word for seas. Early astronomers named them seas because they looked like dark water from Earth. They were not water at all. They were ancient, cooled lava, but hidden inside that story is something remarkable. When volcanoes erupt, they do not release only lava. They also release gases. On Earth, volcanic eruptions push out carbon dioxide, sulfur, and large amounts of water vapor. Water vapor is water in the form of a gas, invisible but real, rising into the air with the heat of the eruption. Scientists believe the moon's ancient volcanoes did something very similar. As magma, the hot liquid rock deep inside the moon, rose toward the surface and erupted. It carried dissolved gases with it. And among those gases was water vapor. The moon had no thick atmosphere to hold those gases close. The vapor simply rose and spread across the surface in thin, ghostly clouds. Some of it drifted into space, lost forever. But some of it, scientists believe, may have traveled toward the poles. There, in the the cold dark of the permanently shadowed craters, it could have settled and frozen. It could have become part of the ice that still sits there today, patient and still, waiting billions of years to be found. This is one of the most striking ideas in lunar science. The water hiding in the moon's coldest shadows may have come, at least in part, from the moon's own volcanic past. The moon may have watered itself. Researchers have studied ancient volcanic deposits on the lunar surface and found evidence of this process. Tiny glass beads found in lunar soil, brought back to Earth by Apollo astronauts, contain traces of water and other volatile compounds. Volatile compounds are substances that turn into gas easily when heated. These beads formed during ancient eruptions when lava was flung into the air and cooled quickly into small round droplets. The water trapped inside them is a record of what the moon's interior held long ago. Scientists estimate that the moon's volcanic period was most intense between about 3 and 4 billion years ago. During that time, eruptions happened repeatedly, releasing gases across millions of years. The total amount of water vapor released during this long volcanic period may have been significant. Some models suggest it could have been enough to form a thin, temporary atmosphere, a brief breath of gas that clung to the moon before slowly escaping or freezing at the poles. That idea is still being studied, but it fits a pattern that shows up again and again when scientists look at the moon's water. Every source of water on the moon has its own rhythm, its own pace, its own cycle of arrival and loss. Comets arrive in sudden, violent impacts, separated by millions of years. The solar wind delivers water slowly and steadily, molecule by molecule, across deep time, and volcanic activity worked in long pulses, erupting and resting and erupting again over hundreds of millions of years, each cycle releasing another breath of vapor into the lunar sky. These rhythms did not happen one at a time. They overlapped. They layered on top of each other. Volcanic steam was rising from the surface at the same time that comets were striking from above, and the solar wind was quietly building molecules in the soil below. All of these cycles ran together, each one adding its small contribution to the same slow accumulation. The moon we see tonight is the product of all of those cycles. Every grain of ice in its shadowed craters carries a history. Some of that ice arrived from the outer solar system on the back of a comet. Some was assembled, atom by atom, from the solar wind, and some rose up from the moon's own deep interior, carried by fire, released as steam, and eventually frozen in the dark. The moon has been gathering water for a very long time, and it has been doing it in more ways than anyone first imagined. The moon is not quite as empty as it looks. When you gaze up at it on a clear night, it seems like a bare, silent world. No clouds, no wind, no weather of any kind. But the moon does have something surrounding it. Scientists call it an exosphere. That is a layer of gas, so thin it barely counts as an atmosphere at all. The particles in it are so spread apart that they almost never touch each other. On Earth, the air around you is thick, with molecules bumping and colliding constantly. On the moon, those same particles would drift for miles before ever meeting another one. And yet, that thin breath of gas is real. It is there, and water plays a quiet role inside it. The lunar exosphere contains several different kinds of molecules. Some come from the solar wind, which is the steady stream of charged particles that flows outward from the sun. Some come from tiny meteorites that strike the surface and kick up dust and gas. And some, scientists believe, come from water ice itself. When sunlight strikes the edges of the moon's shadowed regions, it can break apart water molecules sitting near the surface. Those broken pieces, hydrogen and oxygen atoms, drift upward into the exosphere and float there for a time before settling back down or escaping into space entirely. This process has a name. Scientists call it photodissociation. That simply means light breaking something apart. The sun's ultraviolet rays, which are a form of light too energetic for human eyes to see, carry enough energy to snap the bond between a hydrogen atom and an oxygen atom. Water becomes something else, and those pieces scatter. But here is the quiet wonder of it. Some of those scattered pieces find their way back. Hydrogen and oxygen atoms drifting through the exosphere recombine. They can meet again and form new water molecules. And those new molecules can drift down toward the surface, especially toward the cold poles, where they may eventually settle into the shadowed craters and freeze. The moon's thin exosphere is not just a place where water is lost. It is also a place where water travels. This makes the exosphere a kind of slow, silent transport system. It connects the sunlit parts of the moon to the dark parts. It links the surface to the space just above it. Water does not simply sit still on the moon. It moves in the smallest possible amounts through this thin surrounding layer. The moon's nearest neighbor in this story is, of course, Earth. Our planet sits about 239,000 miles away on average, close enough that the two worlds have shaped each other for billions of years. Earth's gravity keeps the moon locked in its orbit. The moon's gravity pulls at Earth's oceans, creating the tides that rise and fall along every coastline on the planet. These two worlds are in a constant, slow conversation. And that relationship matters for the moon's water, too. Earth's magnetic field, which is an invisible shield generated deep inside our planet's core, extends far out into space. It forms a protective bubble called the magnetosphere. Most of the time, the moon sits outside this bubble, exposed to the full force of the solar wind. But for a few days each month, as the moon moves through its orbit, it passes through the far tail of Earth's magnetosphere. During those days, the moon is briefly sheltered. The solar wind eases, and some scientists believe this monthly shelter may slightly change the rate at which water molecules are created or destroyed on the lunar surface. The moon is not isolated. It exists inside a web of forces. The sun pushes against it. Earth pulls at it. Meteorites strike it. The exosphere above it breathes in and out with each lunar day. All of these forces touch the water hidden in its craters. Even the moon's neighbors farther out in the solar system have played a role. The giant planets, Jupiter and Saturn, have spent billions of years steering comets and asteroids with their enormous gravity. Some of those redirected objects eventually reached the inner solar system. Some of them struck the moon. Each one carried ice. Each one added to the slow, patient accumulation happening in the dark. Nothing on the moon exists in isolation. The ice in those ancient craters is connected to the solar wind, to Earth's magnetic field, to the distant giants of the outer solar system, and to the thin, nearly invisible layer of gas drifting just above the surface. The moon breathes softly, and its breath carries traces of water, moving quietly through the dark. For a long time, scientists could only guess at what was hiding in those dark, cold craters. They had measurements from orbit. They had readings from instruments passing overhead, but they had never reached down and touched the ice directly. That changed on October 9, 2009, when NASA sent a spacecraft to crash into the moon on purpose. The mission was called LCROSS, which stands for Lunar Crater Observation and Sensing Satellite. The plan was simple and bold. Scientists would aim a heavy rocket stage at a permanently shadowed crater near the moon's south pole. Let it slam into the surface, and then fly a second spacecraft through the cloud of debris that rose up from the impact. That second spacecraft would measure exactly what came out of the ground. The target was Cabeus Crater. It sits near the lunar south pole, and its floor has not seen sunlight in billions of years. The temperature inside Cabeus stays near negative 370 degrees Fahrenheit. That is close to the coldest temperature anything can reach. It is one of the coldest places in the entire solar system, colder than the surface of Pluto on most days. The rocket stage hit the surface at roughly 5,600 miles per hour. The impact blasted a crater about 20 meters wide and sent a plume of dust and debris shooting upward into the sunlight. For a few brief moments, material that had been locked in frozen darkness for billions of years was suddenly exposed to space. The LCROSS spacecraft flew through that plume and measured everything it could before it too struck the surface just 4 minutes later. What the instruments found was extraordinary. The plume contained water, not just a trace, not just a hint, but a clear and measurable amount. Scientists estimated that the impact released about 155 kilograms of water vapor and ice. That is roughly the weight of 2 adult humans, released in a single violent moment from a patch of ground that had been frozen and still since before the earth had continents. But water was not the only thing LCROSS found. The plume also contained a surprising mix of other compounds. Scientists detected carbon monoxide, carbon dioxide, and a form of sulfur dioxide. They found traces of ammonia, ethylene, and methanol. The crater floor was not just holding water. It was holding a complex chemical record of everything that had ever been delivered there, layer by layer, over billions of years. This was one of the most striking findings of the entire mission. Cabeus Crater had acted like a cold trap, a place so permanently frozen that almost nothing could escape once it arrived. Every comet that ever struck nearby, every asteroid carrying frozen gases, every solar wind particle that drifted down and bonded with the soil left something behind. The crater floor was a kind of frozen archive, preserving chemistry that would have been destroyed anywhere else on the moon. The amount of water ice detected in the plume suggested that the soil inside Cabeus contained roughly 5 to 8% water by mass in the areas sampled. That number surprised many scientists. Before LCROSS, some researchers expected to find only thin coatings of ice, scattered and sparse. Instead, the data pointed to concentrations that were genuinely significant, more than enough to be worth studying seriously. The LCROSS mission also helped confirm something that orbital measurements had only suggested. The water in these craters was not sitting on top of the surface like frost on a window. It was mixed into the soil itself, bound up with the dust and rock, frozen in place at depths where sunlight could never reach. Getting to it would require digging, but it was there. The impact itself was visible from Earth through large telescopes, though the plume was smaller than some had hoped to see with the naked eye. What mattered was not the spectacle. What mattered was the data streaming back in the minutes before the second spacecraft hit the ground. In those 4 minutes, LCROSS answered a question that had been open for decades. There is water on the moon, not as a theory, not as a possibility, as a measured, confirmed physical fact. The crater that held this secret for billions of years gave it up in a single morning. A spacecraft built by human hands, traveling at more than a mile per second, reached into one of the coldest and darkest places in the solar system and brought back proof. The moon had been keeping this quiet for a very long time, and when it finally spoke, it said more than anyone expected. India was listening too. While LCROSS was making its dramatic plunge into Cabeus crater, another spacecraft had already been quietly circling the moon for months. It was called Chandrayaan 1, which means moon craft in Sanskrit. India launched it in October of 2008. It carried instruments from several countries, including a sensor built by NASA called the Moon Mineralogy Mapper, or M3 for short. That instrument was designed to study the minerals on the lunar surface by reading the light that bounced off the ground, and in that reflected light, it found something extraordinary. Water, not just in one place, not just near the poles. Water signals were showing up across wide stretches of the lunar surface, including regions that received direct sunlight. This was not what anyone had fully expected. Scientists had focused so much attention on the cold, dark craters at the poles that the idea of water existing in sunlit areas seemed almost impossible. Sunlight should destroy water molecules quickly, breaking them apart through a process called photodissociation, where light energy splits the hydrogen and oxygen atoms apart. And yet the M3 instrument kept seeing the signature of water and hydroxyl, which is a molecule made of one hydrogen atom and one oxygen atom bonded together. The signal was strongest near the poles, as expected, but it was present at lower latitudes too. This told scientists something important. Water on the moon was not just hiding in frozen pockets deep inside shadowed craters. It was part of something more widespread, more active, more dynamic than the simple picture of ice sitting still in the dark. The Chandrayaan 1 findings were published in September of 2009, just weeks before the LCROSS impact. 3 separate science teams, working independently with data from 3 different instruments, all reached the same conclusion. different tools built by 3 different groups all point at the same answer. That answer becomes very hard to argue with. The scientific community took notice. One of the most quietly remarkable details from Chandrayaan-1 was what the data suggested about the time of day. The water signal appeared to change depending on the lunar hour. Near the equator, the signal was slightly stronger in the cooler parts of the day, during the lunar morning and evening, and slightly weaker at midday when the sun was highest and the surface was hottest. This hinted at something almost alive in its behavior. Water molecules might be moving across the surface, hopping from grain to grain of lunar soil as temperatures shifted. Scientists call this process migration. The molecules do not stay in one place. They drift, guided by temperature and light, until they find somewhere cool enough to settle. This idea changed how researchers thought about the whole lunar water system. It was not a static thing, frozen in place since the ancient past. Parts of it were in slow, constant motion, tiny amounts of water, moving across the surface one molecule at a time, over millions of years, gradually finding their way toward the poles, where the cold craters waited to catch them and hold them forever. Chandrayaan-1 also gave scientists their first detailed map of where hydroxyl and water signals appeared across the entire moon. The map showed that the signals were not random. They followed patterns tied to the geology of the surface, appearing more strongly in certain types of soil and rock. This suggested that some of the water might not have arrived from outside at all. Some of it might have formed right there, in the soil itself, through chemical reactions between hydrogen delivered by the solar wind and oxygen already locked inside the minerals of the lunar rock. That is a subtle and beautiful idea. The moon, made of rock and dust, may be quietly making small amounts of water on its own surface, one molecule at a time, using ingredients that rain down from the sun, not liquid water, not even ice, just the faintest chemical trace spread across the skin of the moon like a whisper. The Chandrayaan mission ended in August of 2009, when contact with the spacecraft was lost. It had operated for about 10 months. In that time, it reshaped what humanity understood about the moon, a small spacecraft from a young space program, carrying instruments from around the world, had looked at a world everyone thought they knew, and found it was still holding secrets. The moon does not give up its details easily. It asks for patience. It asks for careful instruments and quiet attention. And when you look closely enough, with the right tools and enough time, it shows you something you did not expect to find. Something small, something subtle, something that changes everything. For decades, the moon was considered a dry, dead world. Scientists were fairly confident about this. The Apollo missions had returned hundreds of pounds of lunar rock and soil, and the samples looked bone dry. No water, no ice, no sign of moisture at all. That conclusion settled into the scientific community like dust settling on the lunar surface, quietly, completely, and for a very long time. But the tools used to study those Apollo samples had a flaw that nobody fully appreciated at first. The rocks were brought back to Earth in containers that were not perfectly sealed. By the time scientists opened them in laboratories, any trace amounts of water that might have been present had already escaped or been contaminated by Earth's own humid air. The samples told scientists a great deal about the moon. But on the question of water, they may have been giving a slightly wrong answer all along. The real shift began not on the ground, but in orbit. Scientists realized that the best way to search for water on the moon was to look from above, using instruments that could read the surface without touching it. This is called remote sensing. A spacecraft carries a detector that measures what kind of light or energy bounces back from the surface below. Different materials reflect light in different ways. Water ice, for example, has a very specific signature. It absorbs certain wavelengths of light that bare rock does not. If you know what to look for, you can read the surface like a kind of language. The first strong hints came from an unexpected source. In 1994, a spacecraft called Clementine was sent to the moon. Its main job was to test military sensor technology, not to search for water, but scientists pointed its instruments toward the permanently shadowed craters near the lunar South Pole and found something curious. The radar signals bouncing back from those those dark regions looked different from signals bouncing off the sunlit surface. The pattern was consistent with what you would expect from ice. It was not proof, but it was a signal worth paying attention to. Then came the Lunar Prospector mission in 1998. This spacecraft carried a device called a neutron spectrometer. The way it worked was elegant. When cosmic rays, which are high-energy particles streaming in from deep space, strike the lunar surface, they knock loose tiny particles called neutrons. Hydrogen slows those neutrons down in a very specific way. So if a neutron spectrometer detects a region where neutrons are moving more slowly than expected, that is a sign that hydrogen is present below the surface. And hydrogen, combined with oxygen, makes water. Lunar Prospector found exactly this pattern concentrated near both poles. The signal was clear and strong. Scientists grew more confident. Something hydrogen-rich was hiding in the cold and the dark. What made these discoveries so striking was how long the moon had been studied before they emerged. Humans had been watching the moon for thousands of years. Galileo sketched its craters in 1609. Spacecraft had been orbiting it since the 1960s. 12 human beings had walked on its surface, and still the water had stayed hidden. It hid in the one place no instrument had looked carefully enough, and in amounts too small and too cold to announce themselves. The challenge was that a signal from orbit is not the same as holding a sample in your hand. Scientists could see the hydrogen signature. They could map where it was strongest. They could build a picture of where water ice was most likely to be, but they could not say with absolute certainty what form the hydrogen was in or how much water it represented. The data pointed strongly in one direction, but science requires more than a strong point. It requires confirmation. This is the patient, careful work that defines how discovery actually happens. It is rarely a single moment of revelation. It is a series of instruments, each one a little more precise than the last, each one asking a slightly sharper question. Clementine saw a hint. Lunar Prospector measured a signal. Chandrayaan confirmed water molecules on the sunlit surface. LCROSS crashed into a shadowed crater, and found ice in the debris cloud, each mission built on the one before it. Each answer opened a new question. The moon was not hiding its secrets out of stubbornness. It was simply waiting for the right question, asked with the right instrument, at the right angle, in the right light. Reading the surface from above takes patience. It takes generations of scientists, each one handing their work to the next. And slowly, over decades, the picture becomes clear. And then came the surprises. Scientists had expected the moon's water ice to sit in neat, concentrated deposits. They imagined it pooled in the deepest shadows of polar craters, thick and layered, like a buried glacier. It made sense. Cold traps hold cold things. Shadows protect ice from the sun. The logic was clean and satisfying. But the moon, as it turns out, does not always follow clean logic. When researchers began studying the data more carefully, they found something unexpected. The ice was not only sitting in deep, dark pockets. It was mixed directly into the lunar soil, scattered through the top layer of dust, and rock like salt stirred into sand. Scientists call this soil the regolith, which is just the loose, broken material that covers the surface of the moon. And inside that regolith, water ice was hiding in plain sight. This was strange. The surface of the moon is a harsh place. In sunlight, temperatures climb to around 260 degrees Fahrenheit. That is hot enough to boil water easily. Ice should not survive there. And yet, evidence gathered by several missions suggested that water molecules were clinging to the surface grains, tucked between tiny particles of rock, sheltered in microscopic shadows, too small to see, but large enough to matter. The moon's surface is covered in billions of these tiny hiding places. Part of the reason ice can survive mixed into the soil comes down to how quickly things happen. When a water molecule lands on a sunlit grain of lunar dust, it does not always escape immediately. For a brief moment, it sticks. If it moves fast enough into a slightly cooler spot before the sun drives it away, it can survive a little longer. Over millions of years, even brief moments add up. Small amounts of water, arriving constantly from comets and the solar wind, can work their way into the soil one molecule at a time. is another piece of this that scientists find genuinely strange. The ice mixed into the regolith is not pure. It is not a clean, clear crystal like the ice in a glass of water. It is mixed with dust, with carbon compounds, with tiny fragments of rock. Some of it may be chemically bound to the minerals in the soil itself, locked into the structure of the rock, rather than sitting freely between grains. This kind of water is called bound water or hydroxyl, which is a water molecule that has lost one of its hydrogen atoms and bonded to the surface material instead. It is water, but not quite water as we usually think of it. This distinction matters more than it might seem. Water you can melt and drink is very different from water locked inside a mineral. Future explorers on the moon will need to know exactly what form the water is in before they can plan how to use it. Heating the soil might release some of it. Chemical processes might free the rest. But it will not be as simple as melting a block of ice. What makes the mixed-in ice even more surprising is where it shows up. Researchers found signs of it not just at the poles, where shadows are permanent and cold is constant, but at middle latitudes too, places that receive regular sunlight. This should not work, and yet the data kept pointing to it. One explanation scientists have explored is that the lunar soil itself acts as a kind of insulator. The very top layer heats up in sunlight, but just a centimeter or two below the surface, temperatures stay much colder. Ice buried even slightly beneath the surface can survive in conditions that would destroy it if it were fully exposed. Think of it like dry ground after a frost. The surface thaws quickly in the morning sun, but dig down just a little, and the frozen layer is still there, protected by the earth above it. The moon works in a similar way. Its surface is a poor conductor of heat, meaning warmth does not travel down through it easily, so the top dust heats and cools with the sun, but the layer just beneath stays in a kind of quiet, stable cold. Water ice mixed into that deeper layer can persist through lunar days that last 2 Earth weeks. This was not what anyone expected to find. The moon was supposed to be simple, dry, dead, and well understood. But the more precisely scientists looked, the more complex chaos, but a quiet, intricate order. Water finding every possible shelter. Ice surviving in places that seemed impossible. The moon holding moisture in ways no one had thought to look for, until finally someone looked. And so the question naturally follows. If water ice can hide just beneath the surface, how far down does it actually go? Scientists have been working to answer that question for years. The tools available from orbit can only see so deep. Radar signals sent down from spacecraft bounce back with information. But reading those signals is not simple. Still, the data gathered so far suggests that lunar water ice is not just a thin skin sitting at the very top of the soil. Evidence points to ice existing at depths of at least a few meters in some polar regions. Some models suggest it could go deeper still, locked into the ancient, compacted layers of dust and broken rock that have built up over billions of years. The moon's surface layer, called the regolith, is made of fine crushed rock and glass, created by billions of years of meteor impacts. It is loose and powdery near the top, but it grows denser and more packed as you go deeper. Water ice mixed into this deeper, denser material would be much harder to dislodge. It would be pressed in among the grains, sheltered from the thin radiation that reaches even the shadowed floors of polar craters. The deeper the ice sits, the more protected it becomes. This is where the connection to other systems becomes clear. The same sun that drives weather on Earth, that stirs the oceans and feeds the forests, also shapes what happens to water on the moon. Solar radiation, the steady stream of energy and charged particles flowing outward from the sun, is one of the main forces that destroys exposed water ice on the lunar surface. When sunlight or solar particles strike a water molecule sitting in the open, they can break it apart. The hydrogen drifts away into space. The oxygen follows. The water is simply gone. But buried ice is shielded from that process. The regolith above it acts like a blanket. Not a warm blanket, but a protective one. The same material that insulates the cold also blocks the radiation trying to reach down from above. So the depth of the ice is not just a measurement. It is a record of survival. Ice that sits deeper has had more protection and more subtly delivered to the moon from multiple sources. Comets and asteroids brought ice from the outer solar system. The solar wind carried hydrogen atoms that combined with oxygen in the soil to form new water molecules. Ancient volcanic eruptions may have released steam that drifted toward the poles and froze. Each of these processes added just a little at a time, and over vast stretches of time, those small additions built up. The permanently shadowed craters at the poles acted as cold traps, collecting and holding whatever water arrived. But some of that water did not stay at the very surface. Over time, scientists believe it worked its way downward. Meteorite impacts stirred the soil, mixing surface material with deeper layers. Tiny temperature shifts caused slow movement within the regolith. Gradually, ice became distributed not just across the surface of the shadowed regions, but through the vertical layers beneath them. This connects the moon to a much larger story. Water is one of the most common molecules in the universe. It forms in cold clouds of gas and dust between the stars. It coats the grains of dust that eventually clump together to form planets and moons. It travels across the solar system, locked inside comets and asteroids, and wherever conditions allow, it finds a way to persist. The moon is simply one more place where water has found shelter and stayed. The depth of that water tells scientists something important. It tells them that the moon has been quietly collecting and storing water for a very long time, not in rivers or lakes or anything we would recognize, but in a slow, patient, hidden way. Grain by grain, layer by layer, the ice building up in the dark over timescales that are almost impossible to imagine. There is something deeply calming about that image. The moon, which looks so still and silent from here, has been doing quiet work for billions of years, gathering water from passing comets, catching hydrogen carried on the solar wind, holding it all in the cold dark beneath its surface. The same sun that warms the earth each morning has been, in its own way, helping to shape what the moon holds deep inside, everything reaching across space to touch everything else. The universe working in ways that are slow and steady and connected, even across the vast distance between a star and its small, frozen, water-holding moon. That water, gathered so slowly and held so carefully, is not simply sitting still. Even in the deep cold of the lunar poles, chemistry is happening. Quiet reactions, slow changes. The ice on the moon is not pure and clean the way we might picture it. It is mixed with dust and minerals and ancient debris. And that mixture means the water is always, in some small way, transforming. Scientists have found that lunar ice is not like the ice in your freezer. It does not form in smooth, clear sheets. Instead, it exists as tiny grains mixed into the soil, bound up with the rocky material around it. This kind of ice is called dirty ice, and it behaves differently than pure frozen water. The minerals and particles surrounding it change how it responds to heat, to radiation, and to the faint traces of charged particles that reach the lunar surface from the sun. One of the most important forces acting on lunar ice is something called space weathering. This is the slow process by which radiation and tiny particles from the sun alter the surface of any airless body over time. On Earth, our thick atmosphere blocks most of this radiation. The moon has no such shield. Every grain of ice near the surface is exposed to a constant, gentle bombardment. Over millions of years, this changes the chemistry of the ice itself. When radiation strikes a water molecule locked in the lunar soil, it can break the molecule apart. The hydrogen and oxygen separate. Some of that hydrogen drifts away into space, but some of it recombines with nearby minerals, forming new compounds. Scientists have detected molecules called hydroxyls on the lunar surface. A hydroxyl is a fragment of a water molecule. Just one hydrogen atom bonded to one oxygen atom. It is water that has been partially broken down, changed by the energy of the sun into something slightly different. This is not destruction. It is transformation. The same energy that breaks water apart can also help create it. When solar wind carries hydrogen atoms to the moon, those atoms can bond with oxygen already present in the lunar soil, forming new hydroxyl molecules, and sometimes new water. The surface of the moon is a slow chemical workshop, quietly building and breaking and rebuilding molecules across vast stretches of time. The temperature of the lunar surface plays a powerful role in all of this. In the permanently shadowed craters near the poles, temperatures can drop to around -250 degrees Celsius. At those temperatures, chemical reactions slow almost to a stop. The ice there is preserved, locked in place, barely changing at all. But at the edges of those shadowed regions, where sunlight occasionally grazes the surface, temperatures swing wildly. These temperature shifts drive the chemistry forward, nudging molecules into new arrangements. Scientists also believe that meteorite impacts stir things up. When a small rock from space strikes the moon, it releases heat and energy. That heat can briefly melt or vaporize nearby ice. The water turns to vapor, drifts across the surface, and then refreezes somewhere colder. Each impact is a small redistribution, moving water from one place to another, mixing it with new minerals, changing its chemistry in tiny ways. Over billions of years, countless impacts have stirred the lunar soil like a very slow, very cold mixing bowl. There is also evidence that some of the compounds found in lunar ice are more complex than simple water. Scientists have detected traces of carbon dioxide, ammonia, and other frozen gases mixed in with the water ice in shadowed craters. These compounds arrived on comets and asteroids, just as the water did. They have been sitting in the cold dark for an extraordinarily long time, slowly interacting with the ice and soil around them. The moon's shadowed craters are, in a sense, cold storage vaults for some of the oldest chemistry in the solar system. What this means is that the ice on the moon carries a record. It holds clues about what the early solar system was made of, what kinds of molecules were drifting through space billions of years ago, and how those molecules behave when they are preserved in extreme cold for an almost unimaginable length of time. Reading that record carefully could tell scientists something profound about where the building blocks of life come from. The moon is changing, even now. Slowly, patiently, grain by grain, the chemistry of its frost is shifting. Molecules breaking apart and forming again. Ice migrating from crater to crater, ancient compounds sitting quietly in the dark, waiting to be understood. The moon has never been as still as it looks. It has always been working in its own quiet way through the long, cold dark of time. Light changes everything on the moon. At the poles, sunlight arrives at a very low angle, almost sideways, skimming along the surface like a stone skipping across water. The sun never climbs high in the polar sky. It just grazes the horizon, casting long shadows that stretch for miles. Some of those shadows never end. The floors of deep polar craters sit in permanent darkness, never touched by sunlight at all. And so the ice inside them survives. At the lunar equator, the story is completely different. There, the sun rises high and burns with full force. There is no atmosphere to soften it, no clouds to filter it, no wind to carry the heat away. The surface at the equator can reach temperatures of around 250 degrees Fahrenheit during the day. That is hot enough to boil water. Any ice that forms near the equator does not last long. The sunlight breaks it apart quickly, scattering its molecules into the thin lunar sky. This difference in light creates two very different worlds on the same small body. The poles are cold, shadowed, and rich with preserved water ice. The equator is blazing, exposed, and almost completely dry. The same moon, the same sunlight, but the angle of that light makes all the difference. Scientists have measured this contrast carefully. Instruments aboard orbiting spacecraft have mapped the moon's surface temperatures with great precision. The warmest spots near the equator glow brightly in thermal readings, radiating heat back into space after each long lunar day. The coldest spots near the poles barely register at all. Some permanently shadowed craters sit at temperatures around -400 degrees Fahrenheit. That is among the coldest surfaces measured anywhere in the solar system. What is remarkable is how close these extremes sit to each other. A few hundred miles from a crater floor that has never seen sunlight, the surface bakes in full solar radiation. The moon holds both of these conditions at once, quietly, without any fuss. It is a world of sharp contrasts, written entirely in light and shadow. The poles also receive not. Because the sun stays so low on the horizon, certain peaks and ridges near the poles catch almost continuous sunlight. Scientists call these peaks of eternal light. They sit just outside the darkest craters, bathed in near constant solar energy. This makes them extraordinary places. Just steps away from the coldest, darkest spots on the moon, these ridges glow in almost unbroken sunlight. A future lunar base near the poles could place solar panels on these ridges and draw steady power, while accessing ice from the shadowed craters just below. The contrast between light and dark at the poles is so sharp that it can be seen in spacecraft images. The sunlit ridges appear bright and pale, almost white, reflecting solar light back into space. The crater floors below them are pure black, swallowed completely by shadow. There is no gradual fade between them. The line between light and dark is clean and absolute. Water ice near the surface at the poles reflects light in a particular way. When sunlight grazes across the polar terrain at a low angle, patches of ice can shimmer faintly, scattering light differently than the surrounding dry regolith, which is the loose, rocky soil that covers the moon's surface. Instruments designed to detect this difference in reflectance have found bright patches in regions where ice is expected to be. The ice is not always visible to the naked eye in photographs, but the light it reflects carries a signature that sensitive detectors can read. Near the equator, the soil reflects a different kind of story. The constant bombardment of solar radiation breaks down minerals in the surface layer. It strips electrons from atoms and slowly changes the chemistry of the uppermost grains. The equatorial soil has been baked and altered over billions of years of direct sunlight. It looks and behaves differently from polar soil, which has spent much of its existence in cold shadow. Even the color of the moon shifts subtly depending on where you look. Polar regions, with their long shadows and preserved ancient material, appear slightly different in tone from the sun-scorched equatorial plains. These differences are small, but they are real, and they carry information. Light in this way is not just something that falls on the moon. It is something that writes on it slowly, over billions of years, leaving a record that patient instruments can read. The moon's surface is a map of its relationship with the sun. Every shadow, every bright ridge, every patch of frost hiding in the dark tells part of that story. And the poles, where light arrives sideways and darkness endures forever, hold the most remarkable chapters of all. The moon tilts only slightly on its axis. That tilt is just about 1.5 degrees. On Earth, our axial tilt is about 23.5 degrees, and that tilt is what gives us seasons. Summer arrives when our hemisphere leans toward the sun. Winter comes when it leans away. The moon, with its tiny tilt, has almost none of that. It barely nods toward the sun at all, and that small difference changes everything about where water can survive. Because the moon barely tilts, sunlight at the poles arrives almost horizontally. It skims across the surface at a very low angle, like a flashlight held nearly flat against a table. The light grazes the tops of crater rims and the edges of ancient ridges. It never reaches down into the deep, bowl-shaped floors below. The craters near the poles are shaped in just the right way to trap permanent darkness. And permanent darkness, as we have seen, is where ice endures. On Earth, even our coldest places warm up a little in summer. The axial tilt guarantees that. But the moon's poles receive no such seasonal rescue. There is no summer tilt to bring the sun higher in the sky. The shadows stay. The cold stays. The ice stays. The moon's tiny tilt is not a flaw in its design. It is the very reason its water has survived for billions of years. Scientists have measured the moon's tilt carefully using laser instruments and orbital tracking. The precision of those measurements is remarkable. They can detect changes in the moon's orientation down to fractions of a degree. And what those measurements confirm is that the moon is extraordinarily stable. It does not wobble much. It does not swing through wide seasonal arcs. It holds its position with quiet steadiness, and that steadiness protects the ice at its poles like a careful hand cupped around a small flame. Now, the moon is silent in the way that space is silent. Sound needs a medium to travel through, and the moon has almost no atmosphere to carry it. not the same as stillness. The moon vibrates. It rings. It hums with energy that instruments can detect and translate into something we can hear. Scientists have converted seismic data from the moon into audio signals, and what they found was extraordinary. The moon rings like a bell when struck. During the Apollo missions, astronauts deliberately crashed the upper stages of their rockets into the lunar surface. The moon vibrated for hours afterward. It rang and rang, slowly fading, in a way that solid rock on Earth never would. Scientists believe this ringing happens because the moon's interior is very dry and rigid in certain layers, allowing vibrations to bounce around for a long time without being absorbed. Those same seismic instruments detected something else. Moonquakes, small tremors that ripple through the lunar crust. Some are caused by the tidal pull of Earth's gravity, which gently squeezes and stretches the moon as it orbits. Others happen near the surface, possibly caused by the extreme temperature swings between lunar day and night. The surface heats to over 250 degrees Fahrenheit in sunlight, then plunges to nearly 300 degrees below zero in darkness. That kind of thermal stress cracks rock. It shifts grains of soil. It creates tiny movements that sensitive instruments can feel. Near the poles, those temperature swings are far less extreme. The permanently shadowed craters stay cold and still. They do not crack and shift in the same way. They are among the most stable environments on the entire moon. And that stability is part of why the ice inside them has survived. The ice does not get shaken loose. It does not get cracked open and exposed to the sun. It simply rests undisturbed in the deep cold. The moon's tilt, its vibrations, its quakes, its temperature swings, all of these forces work together in a slow, quiet system. The tilt determines where light falls. The light determines where heat builds. The heat determines where ice can and cannot survive. The quakes and thermal cracks shape the surface over time, slowly mixing and rearranging the uppermost layer of soil. Everything connects. The moon is not a dead, frozen object sitting passively in space. It is an active system, responding to forces from the sun, from Earth, from its its own interior from the ancient history of its formation, and the water hidden inside it is not separate from that system. It is part of it, shaped by every one of those forces, preserved by the precise and fortunate tilt of a world that barely leans at all. When sunlight touches the moon's surface, something quiet and precise begins to happen. The physics behind it follows rules that never change. Simple rules, elegant ones, and they explain exactly why water on the moon is so fragile and so fascinating. Water is made of 2 hydrogen atoms and 1 oxygen atom. That small, simple structure is one of the most important shapes in the universe. But it is also a delicate one. When sunlight hits a water molecule sitting exposed on the lunar surface, the energy from that light can break the molecule apart. This process is called photodissociation, which means light splitting something into pieces. The ultraviolet part of sunlight, the high energy portion we cannot see with our eyes, carries just enough energy to snap the bond between the hydrogen and oxygen atoms. In a fraction of a second, a water molecule that may have traveled millions of miles to reach the moon simply stops being water. The numbers behind this are striking in their precision. Scientists calculate that an exposed water molecule on the sunlit lunar surface survives for only about a few hours before ultraviolet light destroys it. Some estimates place that window even shorter, closer to a single hour near the lunar equator, where sunlight strikes most directly. An hour. That is all the time a water molecule gets before the sun claims it. The moon has no thick atmosphere to filter that radiation, no ozone layer to absorb the harshest wavelengths. The surface sits completely open to space, and the sun's full energy arrives unblocked. Once the molecule breaks apart, the hydrogen atoms are so light that the moon's gravity cannot hold them. The moon's gravity is about 1/6 of Earth's, and that lower pull means gases escape far more easily. The freed hydrogen drifts upward and is eventually lost to space. The oxygen may briefly bond with minerals in the soil, or it too may drift away. Either way, the original water molecule is gone. It cannot reassemble itself on its own. The chemistry does not reverse simply because the sun moves on. This is why the geometry of sunlight on the moon matters so much. The moon rotates slowly, completing one full turn every 27.5 days. That is the same amount of time it takes to orbit Earth, which is why we always see the same face of the moon from our planet. Because the rotation is so slow, any given spot on the equator spends about 2 weeks in full sunlight. 2 weeks of continuous ultraviolet bombardment. No water molecule could survive that exposure. The math makes survival at the equator essentially impossible for surface ice. But the poles are different. The moon's tilt is only about 1.5 degrees from perfectly upright. On Earth, our 23.5 degree tilt creates our seasons. The moon's near-zero tilt means the sun always hangs low on the horizon at the poles, skimming across the sky rather than rising high overhead. Some crater floors at the poles are angled in such a way that sunlight never reaches them at all. Not for a day, not for a season, not for billions of years. The geometry of the moon's orbit, its tilt, and the shape of those craters combine to create permanent shadow. And in that shadow, photodissociation cannot happen. The ultraviolet light never arrives. The water molecules are safe. Scientists can calculate exactly how much of the lunar surface sits in permanent shadow. The answer is roughly a few percent of the polar regions, small pockets of eternal darkness scattered across the landscape. These regions have been mapped carefully using orbital spacecraft. The math of light and shadow, the angles of crater walls, the precise tilt of the moon, all of it can be modeled and predicted. And those predictions match what the instruments find. Where the models say shadow should exist, ice signatures appear. Where the models say sunlight reaches, the ice is gone. There is something quietly wonderful about that agreement. The universe follows rules, and those rules are consistent enough that scientists sitting on Earth can calculate where ice should exist on a world nearly 400,000 kilometers away, and then send a spacecraft to confirm it. The numbers work. They always work. The same physics that governs a water molecule breaking apart in an hour also governs the orbit of the moon. The angle angle of its tilt, the depth of a crater's shadow. It is all one connected system, running on the same simple laws, producing outcomes that can be measured, predicted, and understood. The sunlight that destroys water on the moon is the same sunlight that warms our faces here on Earth. The difference is simply geometry. And geometry, it turns out, is everything. Geometry shapes everything on the moon. But geometry alone does not explain why any water survives there at all. The fact that it does is something close to remarkable. Think about what water on the moon must endure. The lunar surface has no thick blanket of air to protect it. There is no weather to move moisture from place to place. There is no ocean to store heat and release it slowly. The moon is exposed, bare, and ancient. And yet, in the coldest corners of its polar craters, water ice holds on. It has been holding on for a very long time. The system that allows this is fragile in ways that are hard to fully picture. Water arrives on the moon from many sources. Comets carry it in. Asteroids deliver it. The solar wind, that constant stream of charged particles flowing out from the sun, helps create it through chemical reactions in the soil. Once water molecules form or land on the surface, they begin to move. Sunlight heats the surface and sends those molecules hopping across the ground in short, quick jumps. Scientists call this process migration. The molecules do not stay where they land. They drift slowly and randomly across the face of the moon. Most of them do not survive. A water molecule that hops into a sunlit area breaks apart quickly. The sun's ultraviolet light, that high-energy radiation invisible to our eyes, tears the molecule into its parts. The hydrogen drifts away into space. The oxygen bonds with something else. The water is simply gone. This happens within hours of exposure. The moon loses enormous amounts of water this way, constantly, every single day. But some molecules are lucky. Through the randomness of their movement, they drift toward the poles. They hop closer and closer to the deep craters where sunlight never reaches. And when a molecule finally crosses into that permanent shadow, it stops. The temperature drops so low, sometimes below -200 degrees Celsius, that the molecule has no energy left to move. It settles into the soil. It freezes. It stays. This process has been happening for billions of years. Each molecule that survives the crossing adds to the ice that has quietly built up in those shadowed basins. The ice we find today is the result of countless tiny arrivals, countless tiny survivals across an almost unimaginable stretch of time. What makes this balance so fragile is how precisely it depends on conditions staying just right. The moon's axial tilt, the angle at which it leans as it orbits the Earth, is only about 1.5 degrees. Earth's tilt is about 23.5 degrees. And that tilt is what gives us our seasons. The moon's tiny tilt means its poles receive sunlight at a very low angle, almost sideways, and the floors of deep craters never catch any sunlight at all. If the moon tilted even a few degrees more, those shadowed regions would shrink. Sunlight would creep further into the craters. The ice would be exposed. It would not last. Scientists have found evidence suggesting the moon's tilt may have changed over its long history. In its earliest years, the moon may have been more active, with volcanic eruptions and shifting interior forces that could have altered its orientation slightly. Some researchers believe the poles may have wandered over time, a process called true polar wander, where the entire body slowly reorients itself. If the poles shifted, the shadowed craters shifted with them. Ice that was once protected may have been exposed and destroyed. New regions may have fallen into permanent shadow and begun collecting ice fresh. The ice we find today may not be the same ice that formed in the same places billions of years ago. This adds another layer to the story. The lunar ice is not simply ancient and unchanging. It is the product of a long, slow, ongoing process. Delivery and loss, freezing and drifting, survival and destruction. The balance tips slightly one way, then slightly another across geological time. There is something quietly moving about that image. A single water molecule, born from a collision between hydrogen and oxygen in the lunar soil, drifting slowly across a world with no air and no ocean, hopping from grain to grain of ancient rock dust, until by chance it reaches a place it possible. And in the universe, possible is often enough. And yet, for all we have learned, the moon keeps its secrets close. Scientists have confirmed that water ice exists near the lunar poles. They have measured it, mapped it, and even tasted it in the plume of a deliberate crash. But the deeper questions, the ones that really matter, are still wide open. And that is not a failure. That is an invitation. One of the biggest mysteries is simply this: how much water is actually there? The estimates vary widely. Some scientists believe there may be hundreds of millions of tons of ice locked inside permanently shadowed craters. Others think the true number is far smaller. The instruments we have sent to the moon so far can only see the surface or just beneath it. What lies deeper, buried under meters of ancient dust and rock, remains largely unknown. We have glimpsed the edge of something. We have not yet seen its full shape. The exact age of the lunar ice is another open question. Some of the water molecules resting in those cold, dark craters may have arrived billions of years ago, carried by comets that struck the early moon. Other molecules may be far younger, delivered by solar wind interactions or recent asteroid impacts. Right now, scientists cannot easily tell the difference. The ice does not come with a label. Developing tools that can read the age of individual water molecules in lunar soil is one of the quiet frontiers of planetary science today. There is also the question of distribution. We know ice exists at the South Pole. Evidence suggests it exists at the North Pole too, but the two poles are not identical. The craters are different shapes. The shadows fall differently. The history of impacts at each pole is its own story. Scientists are still working to understand why the ice seems to be spread unevenly, why some craters appear rich with frost, while others nearby seem almost dry. The answer likely involves the specific geometry of each crater, the angle of the sun, and the long history of material being delivered and lost. But the full picture has not yet come into focus. Then there is the question of what else is mixed in with the ice. The LCROSS mission found water, yes, but it also found carbon monoxide, ammonia, and traces of other compounds in the plume. These chemicals tell a story about where the material originally came from and what processes shaped it over time. Scientists are still reading that story carefully. Each compound is a clue. Together, they may reveal which sources, comets, asteroids, solar wind, volcanic activity contributed most to the water we see today. Sorting out those contributions is painstaking work, and it is far from finished. Perhaps the most profound open question is one that connects the moon to the rest of the solar system. The same processes that brought water to the moon may have brought water to Earth. Comets and asteroids that seeded the lunar poles with ice were also striking our young planet. The chemistry of lunar water, if we can read it precisely enough, may carry fingerprints that tell us something about where Earth's own oceans came from. The moon has been sitting in our neighborhood for 4.5 billion years, collecting evidence. It is, in a sense, a record keeper. And we are only beginning to learn how to read its records. Scientists also want to understand how stable the lunar water really is over long timescales. We know that water molecules can be lost to space when sunlight breaks them apart. We know that polar wander and shifting shadows can expose ice that was once protected, but the precise rate of loss and how it balances against the rate of new delivery is still being calculated. The moon is not a static place. It is changing slowly across millions of years. Understanding that change requires more data than we currently have. What makes all of this exciting rather than frustrating is the simple fact that the tools to answer these questions are coming. New missions are being planned. Rovers designed to drill into the lunar surface and sample ice directly are in development. Instruments that can measure the chemistry of individual grains of soil are being refined. The moon is close enough to reach. The questions are specific enough to test. That combination, proximity and clarity, is rare in space science. The moon has been overhead every night for all of human history. People have looked up at it, wondered about it, written poems about it, and navigated by its light. And still, it holds surprises. Still, it offers new things to learn. That quiet persistence, that willingness to keep revealing itself slowly, is part of what makes the moon such a remarkable companion in the night sky. One of the most practical reasons scientists care so deeply about lunar water has nothing to do with drinking it. It has to do with leaving Earth behind. Water is made of two elements, hydrogen and oxygen. Those same two elements, when separated and stored as liquid gas, become rocket fuel. Liquid hydrogen burns. Liquid oxygen feeds that burn. Together, they produce one of the most powerful propellants ever used in spaceflight. The engines that launched the Saturn V rockets, the ones that carried astronauts to the moon in the late 1960s and early 1970s, ran on exactly this combination. Carrying all that fuel from Earth is enormously expensive. Every kilogram launched from Earth's surface costs thousands of dollars just to lift into orbit. The weight of fuel needed for a long mission multiplies that cost quickly. But if water already exists on the moon, and if we can extract it and split it into hydrogen and oxygen, then the moon becomes something remarkable. It becomes a fuel station. Scientists call this idea in situ resource utilization. In simple terms, it means using what is already there. Instead of shipping everything from home, future missions could harvest what the moon provides. Water ice in the permanently shadowed craters near the poles could be mined, melted, purified, and then broken apart using electricity. That electricity could come from solar panels positioned on the sunlit crater rims nearby, where sunlight never stops. The process of splitting water into hydrogen and oxygen using electricity is called electrolysis. It is not a new idea. We do it in laboratories on Earth regularly, scaling it up to work on the moon, in a vacuum, in extreme cold, with robotic systems operating largely on their own, is the engineering challenge. But the chemistry itself is well understood. The physics is solid. What remains is the building. A lunar fuel depot would change the math of deep space travel entirely. A spacecraft leaving the moon requires far less energy than one leaving Earth. The moon's gravity is about 1/6 of Earth's. That means a rocket needs far less fuel to escape the moon's pull. If that rocket is already fueled with hydrogen and oxygen made from lunar launching point for missions to Mars, to the asteroid belt, and beyond. Mars is the next obvious destination. A crewed mission to Mars, using fuel made partly on the moon, could reduce the total mass that needs to be launched from Earth by a significant amount. Some estimates suggest that lunar-derived propellant could cut mission costs dramatically, though exact figures depend on the technology used and how much water can realistically be extracted. The potential is large enough that space agencies and private companies are both studying it seriously. Beyond Mars, the same logic applies further out. The outer solar system, with its moons covered in ice and its gas giants wrapped in storms, has always seemed impossibly far. But distance in space is partly a fuel problem. More fuel, more range. If the moon can supply that fuel, the outer planets become less unreachable. Now think further ahead. Not decades, but millions of years. The sun will slowly grow brighter over the next billion years. Earth's climate will warm. Eventually, far in the future, the sun will expand into a red giant, a star that swells to many times its current size. When that happens, the inner solar system will change beyond recognition. The moon will still be there, though, tidally locked, slowly drifting outward in its orbit at a rate of about 3.8 centimeters per year. By the time the sun begins to expand, the moon will be noticeably farther away than it is today. What happens to the lunar ice in that distant future is hard to say. As the sun brightens, even the permanently shadowed craters may eventually lose their protection. The ice that has rested quietly in those cold, dark basins for billions of years may finally begin to escape. It would drift into space as vapor, carried away by the solar wind, scattered across the solar system in molecules too thin to see. But even that is not an ending. Those water molecules, broken apart and spread across space, become part of the raw material drifting between the stars. In time, some fraction of them may find their way into a new cloud of gas and dust. That cloud may collapse under its own gravity. A new star may form. Around it, new worlds may gather, and somewhere on one of those worlds, in some form we cannot predict, those ancient molecules of lunar water may become part of something new. The universe does not waste what it makes. It only transforms it. That thought is worth sitting with for a moment. The water on the moon is ancient. It has traveled across the solar system, survived billions of years of cold and silence, and now it sits waiting in the dark. And we are beginning to think seriously about what to do with it. For a long time, the moon felt like a place to visit, not a place to stay. The Apollo astronauts landed, walked, collected rocks, and came home. Their missions lasted only a few days. They carried everything they needed with them, including every drop of water. The idea of living on the moon, of building something permanent there, seemed like a dream too far away to plan for. Water changes that entirely. Carrying water from Earth to the moon costs an enormous amount of energy and money. Every kilogram launched into space requires powerful rockets and tremendous fuel. Scientists estimate that launching 1 kilogram of anything to the lunar surface costs tens of thousands of dollars. Water is heavy. A single person needs roughly 2 to 3 liters of water per day just to survive, and far more when you account for hygiene, food preparation, and cooling systems. Supplying a moon base from Earth alone would be staggeringly expensive. But if water already exists on the moon, the math begins to change. A base near the lunar South Pole could potentially access ice in the permanently shadowed craters nearby. Rovers or robotic miners could extract that ice, melt it, and purify it. That water could sustain a crew. It could grow food in sealed greenhouses. It could be split into hydrogen and oxygen, providing breathable air and rocket propellant all at once. The moon stops being a destination that drains resources and starts becoming a place that offers them. NASA's Artemis program is already planning with this in mind. The program aims to return humans to the moon and establish a long-term presence near the South Pole, precisely because of the ice. The Lunar Gateway, a small space station planned to orbit the moon, is designed to support missions that will study and eventually use those polar resources. Several space agencies around the world, including those of China, Europe, India, and Japan, are developing their own lunar exploration attention from many directions at once. There is something quietly remarkable about this moment. For all of human history, the moon has been a light in the sky. People have watched it, measured time by it, written poems about it, and used it to navigate the sea. Ancient farmers planted crops by its phases. Ancient sailors read its position to find their way home. The moon has always been part of human life, even from a distance of nearly 385,000 kilometers. Now we are learning that it holds water, and that water connects the moon to something much larger than our own plans for it. The ice in those shadowed craters likely arrived from many places. Some came from comets that formed in the cold outer reaches of the solar system, built from the same ices that gathered when the planets were young. Some came from asteroids that carried water locked inside their minerals. Some was made right on the lunar surface when hydrogen from the sun bonded with oxygen in the soil. Every source tells a different part of the same long story, the story of how water moves through the solar system, how it gathers and hides and waits. We are made of water. Our bodies are roughly 60% water by weight. The oceans that cover most of our planet formed from the same kinds of sources that delivered ice to the moon. Comets and asteroids brought water to early Earth, just as they brought it to the lunar surface. The water you drink today has been cycling through the Earth for billions of years. It has been rain and river and ocean and ice and vapor and rain again. It has passed through living things beyond counting. And now we find that same water in frozen form, resting quietly in the dark at the top of the world that circles us. There is a kind of deep connection in that. The moon is not separate from our story. It formed from the same collision that shaped the early Earth. It has been our companion through every era of life on this planet. And the ice hidden in its craters is made of the same atoms that flow through every living thing on Earth. Building a home on the moon would not be leaving Earth behind. In a quiet way, it would be carrying a piece of Earth's oldest story forward into the dark, and finding that the dark was already holding something familiar, waiting patiently for us to arrive. And so we arrive at the end of this this long, quiet night of discovery. We began with a moon that seemed dry and lifeless, a pale stone hanging in the dark, something beautiful to look at, but empty of the things we associate with life and possibility. For most of human history, that was the story we told ourselves about it. That story has changed. We now know that the moon holds water ice in its deepest, coldest craters, ice that has been sitting in perfect darkness for hundreds of millions of years. Ice that arrived on the backs of comets and asteroids and was perhaps breathed out long ago by ancient volcanoes. Ice that the solar wind helped build, atom by quiet atom, over vast stretches of time. The moon kept this secret well. It took spacecraft crashing into the surface, orbiting instruments measuring reflected light, and generations of scientists studying data from millions of miles away to finally see what was there. And what was there was water, ordinary, remarkable water. There is something deeply settling about that. The universe is not a cold and random place, though it can seem that way when you look at the numbers. The distances are enormous. The timescales stretch beyond anything the human mind can truly hold. And yet, again and again, the same ingredients appear. Water shows up on moons and comets and asteroids and planets. Carbon forms the same kinds of molecules in clouds of gas between the stars as it forms in living cells here on Earth. The building blocks of life are not rare. They are scattered everywhere, patient and persistent. The moon is close enough to touch in cosmic terms. It is 250,000 miles away, which sounds like a great distance until you consider that the nearest star beyond our sun is about 25 trillion miles away. The moon is our neighbor. It is practically in our backyard. And in that backyard, there is ice. There is the raw material for water, for air, for fuel. There is the possibility of a foothold. Future explorers will walk into those shadowed craters. They will drill into the frozen ground and pull up samples that have not seen sunlight since before the dinosaurs walked the earth. They will study that ice and learn more about where our water came from, and perhaps about where life's ingredients have traveled across the solar system. Every sample will be a message in a bottle, sent from the early solar system, and waiting all this time to be read. is the future, and the future can wait. Right now, the moon is rising somewhere over the earth. It is casting its soft silver light across oceans and deserts and sleeping cities. It is doing what it has always done, pulling gently at the tides, keeping the earth's tilt steady, watching over the long, slow turning of life on this small blue world. And in its craters, in the deep cold dark at its poles, the ice is resting, perfectly still, perfectly quiet. The earth is spinning beneath you right now, slowly, steadily, the way it has for 4.5 billion years. The oceans are moving in their great slow circles. The atmosphere is breathing in and out with the seasons. Somewhere above you, the moon is tracing its patient arc across the sky. The same arc it has traced since before the first living thing opened its eyes on this planet. You are part of all of that. The water in your body is ancient. It has been part of oceans and clouds and rivers and ice sheets. It has passed through creatures that lived and died long before humans existed. And now it is here in you on this night, as you listen to the quiet story of a frozen moon. The universe is very large. You are very small, and somehow that is not frightening. It is a comfort. You are held inside something immense and old and full of quiet order. Stars are forming right now in distant clouds of gas and dust. Planets are cooling. Ice is resting in dark craters on worlds we have not yet visited. And here, on this one small world, someone is drifting toward sleep, wrapped in the warmth of everything that had to happen for this moment to exist. The moon is out there tonight. The ice is waiting. The long road ahead is full of wonder, and you can rest now. Subscribe for a brand new space topic every night. One tap, and something incredible is waiting for you tomorrow. Sweet